Good morning. Yes, we have a class today. That's right, Wilson. No worries, Matt. We are here. We will get everybody here. All right, you guys can see the screen well? Thank you. Oh, is Mickey here? There is no reason to cheat, Wilson. Well, I think Mickey is not going to be here today. He's traveling. So I know you have to survive with me only. Oh my gosh. But I will try to keep his style. And there you go.
Sometimes I feel like I don't have a partner. Sometimes I feel like my only friend is the city I live in, the city of angel. Lonely as I am, together we cry. I drive on the streets 'cause she's my companion. I walk through the hills 'cause she knows who I am. She sees my good deeds and she kisses the windy. And I never worry, now that is a lie. I don't ever wanna feel like I did that day. Take me to the place I love. Take me all the way. I don't ever wanna feel like I did that day. Take me to the place I love. Take me all the way. Yeah, yeah, yeah. It's hard to believe that there's nobody out there. It's hard to believe that I'm all alone. At least I have her love. The city, she loves me. Lonely as I am, together we cry. I don't ever wanna feel like I did that day. Take me to the place I love. Take me all the way. I don't ever wanna feel like I did that day. Take me to the place I love. Take me all the way. Yeah, yeah, yeah.
All right. I am sorry to disappoint everyone, but it's just me today. You guys make me feel so good. Anyway, it's almost Berkeley time. So not all is going to be different. There we go.
Welcome, ECS 16A. Woo!
Very good. The moment that I have been waiting for has arrived. I will teach the lecture. As you saw in your schedule, we changed a little bit the order. And the reason is because what we are teaching here is really designing information devices and systems. It's not only linear algebra. So we are giving you tools, and today we are going to start a different set of tools which are related to the circuits. So and I know that lots of people are scared of circuits, others love circuits, and the reason we have this class is to bring everyone to the same level, so that we can start designing the future, really, designing the new systems that people will be using years from now. So announcements. So we don't have many announcements, not much happening in terms of the class. I will send a post on Piazza later with some information about a lecture, a guest lecture that will be given by a researcher at Apple that is prepared for freshmen, for people that are starting their careers in engineering. So I'll send that to you once I have the Zoom link correctly. All right, shall we start then? Okay. The information I'm going to give to you, you will find in note 11. There is 11A and 11B. Most of the things I'll cover here today will be in 11A. I really recommend you read the notes. The notes are quite good. So this picture, for example, I took from there. So what's our class all about? It's good to remember now that we have been in the world of proofs and linear algebra. What we want to do here is really to take problems that we have in the real world and transform that real world after we do some processing into some information. Information that can then be used by others. And sometimes it's just the information to take the next step. Sometimes that information will actually help us to actuate what comes next. So we are going to have to look at some sensors. And from this, these sensors will provide us with data, with signal that we need to understand, we need to process, we need to interpret in order to provide the outcome of this box of 16A, which is the information. So let's start just by thinking about what are the typical analog world problems? What are the things that we have around us that we will, in 16A, have to be thinking about how to design, how to sense, how to process the information in order to eventually have an actuation event. Examples, situations, things that we have around us. You can use the chat, you can unmute yourself and talk. What do we need? What do we have in the world? Come on. We have a phone, right? Does the phone have a sensor? A laptop, a microphone, cameras. There we go. We have cars, houses, displays, you name it, right? Even refrigerators today have all sorts of electronics and sensors that we use. So, okay. I have a few cartoons here. There we go. Now we are talking spy drones. I like that. Sometimes the situations are hospital rooms. And as you know, my research is related to medical devices and MRI. Let's talk about MRI. And I really think that our job as engineers is to make these situations be as efficient as possible, as clean as possible, as sustainable as possible, and comfortable for us humans. I think that's our responsibility here, as you know, we have the brains to deal with the math and the engineering. All right, now sensors. The sensors are many sensors. Do we want to scratch our heads here? Give examples of sensors. Ultrasonic sensors, very good. Light sensor, infrared sensor, that's right. Oh, photoresistors, phototransistor, which I love, you have in the lab. CMOS sensors, microphone, gyro, CCD cameras, very good. We are playing around the lab with imaging, right? Great. So there are many sensors. And today, a lot of the research that is done in sensors is not only to improve the performance of the sensors per se, but also to look at designs and how are we going to integrate all the sensors that we have around us into products, into devices that are good to have, and in a way that the information that you're going to get from those sensors, from that data, is more accurate because of your design. So we have been seeing a lot of efforts on the wearables, for example. Just giving this example because it's close to my research, where people are really thinking carefully of where do you have to place sensors in order to measure the biosignals that you want in order to educate the person on their health status. Self-driving cars, autonomous cars are also a great example of sensors. Both of them require a lot of safety, a lot of robustness on the data, because the actuation part has huge consequences, right? So the design has to be solid at the same time that we want cool things, colorful things, comfortable things. So this is all our jobs, engineers. That's what we do, which is pretty cool. Then once we have these sensors and we have, well, once we have the problem established and we have the sensors, now we are going to process the data. And this is what we have been working on in this class so far. We have been processing we have given you tools that will allow you to formulate a process, to have a language that you can now communicate to the computer, which will really do the processing of the data. So this module that we're going to start is no different. We're just going to establish a language and new tools that will again help us communicate with the computer, which will then process the information that we are giving and do the analysis that we need and the data processing that we need applied to circuits. All right. And then, so this is what this class is. And we always have real world applications in the lab. And also here in class, you will have a real world application, which is the circuits case. The actuation part, you're going to do in 16B. And again, you're going to get the tools, mathematical tools, physical models, and circuits to understand and design the actuation part. Okay, questions so far? All right, I'll move on. I'll give you an example. And this is research that was done in my lab in collaboration with Professor Jan Rabai, in collaboration with a company, and in collaboration and using some of the work that Professor Ricky Muller did in her PhD at Berkeley. This is an example of electromyography, also known for short as EMG. What is the purpose of EMG? EMG, you design electrodes. Electrodes are just connectors that are going to be in touch with your skin to monitor muscle activity. Why do we want to monitor muscle activity? It's mostly for rehabilitation, for people that have somehow lost the ability of moving limbs. Then you want to monitor that muscle activity in order to teach the brain again how to perform that movement. Very important data to have. Today, there are some cool applications that use EMG for gesture recognition, and that can also help people move machines, video games. I have 2 gamers at home, and then this is what they think that is the best application for EMG. But how is EMG done today? And this is really how I would like you guys to look at the world. EMG is done in the most ridiculous way possible. You are going to help someone rehabilitate and regain movement by adding all these electrodes to the skin. They're really bulky electrodes, huge electrodes that are connected by wires to a board where you're going to be collecting the data. In many cases, in these pictures, it's not shown. You have to also carry a power supply, which is a heavy battery. So here I am, I had an accident, I can't walk properly, and I have to carry all these electrodes and wires around me. Of course, it defeats the purpose. That's like the human side and the real world side. Then you look at the data. The data I want to gain, when we move our hands, we have lots of small muscles moving, or when we walk, we have large muscles, we have small muscles, in order to regain the performance that we had. We have to pick up all these signals. Can I pick up signals from small muscles with such large electrodes, such large area? Of course I can't, right? Because I need higher resolution. Okay, so this is an example of a problem. I am sure you can find many others. Then what we came up with was, okay, I'll show you a video of what we came up with. So my group works on flexible electronics, and we wanted to change the way that EMG is done. How? By making the electrodes more comfortable, wireless, and improving the resolution by increasing the number of the electrodes without compromising on the data. Data quality is the #1 of any engineering system. So here is a movie. I'll talk over it so that you get all the parts. So we work in my lab on printed electronics. And as I said, I was collaborating with Professor Jan Rabai. So here is an ink that is silver. It's a conductor that can be made into a flexible conductor if you deposit it in a flexible substrate. We use screen printing, which is the same printing technique that you use for t-shirts, graphics on t-shirts, to deposit this conductor, these wires, these electrodes. So you see the screen printer first spreads the ink, and then it goes and pushes it through a silk screen. And when we come back, there's our design. So we designed an EMG sleeve with 64 electrodes. You can see that it's lightweight and very flexible. Then the students, this is my student team here, could put on the sleeve in his arm. And with that, we had much better resolution and also much nicer contact with the body. Now, this board that you see is what I said that Professor Ricky Muller designed during her PhD here at Berkeley. And the students from Jan Rabai's group were working on this hyperdimension classifier. Oh, it looks very complicated, but you actually learn about it in this class, how to do classification of data. Then you have to train the computer. And that's where your circuits background is going to come about, because you have to tell the computer, hey, computer, this is what you should recognize when I give you this algorithm. This is this element, this is that element. And here you see how the student first trains the computer to have this data classification. And you see here the real-time gesture. Now, this work has been published. I'm happy to give you the big article of all the data. And the students also demonstrated actuation, which is what you learn in 16B, which was after the algorithm was optimized for the system that we designed. They could move cars or lift up things with an artificial arm. And I hope that's the next step of our research will be helping people that are fitted with artificial limbs to gain the real movement. Okay, so it's just an example. And I really hope that this is the engineering spirit that you are going to carry throughout your education. Is we have the brains to change how things are. We just have to look critically, find the right collaborators, find the right skills around us, and change things, make things better. And that can be in many, many areas. But we have to start small, especially when our goal here is to teach a computer how to analyze a circuit. And for example, I could not tell the computer, go find me these 3 elements that I'm showing here, a battery, an LED, a light emitting diode, and a resistor, and build this circuit for me. This is a pretty simple circuit. The computer is not capable of doing that, right? But if I give the computer a model like I drew here, where I say, okay, you have a battery, and then I give the computer a set of commands of what we would, how to analyze the battery. Here I say, okay, you have a diode connected to the battery, and you have a resistor connected to the circuit in a loop, in a closed loop, and that's why it's called circuit, because it needs to be closed in order to work. Now, Mr. Computer, you go and do the analysis that I asked you for. And these are the skills that you're going to learn, okay? But we can build that simple circuit. All we need is a battery. Why does it need to be a 9-volt battery? Because that's what the LED needs in order to work. In your lab kit, you have an LED, right? Didn't you play around with the LED? You have several resistors, because I have the same lab kits that you have. Let's see if I can manage the camera better, okay? So I'm just connecting, just like in that picture there. I have the LED, I have the resistor, and then if I come here and the battery connects to the battery. Things to start paying attention. In the battery is a power source. You will see a positive sign, a negative sign. In our circuits, when we draw it, we are going to have the positive side and the negative side, okay? And we are going to be tracking those positive and negative signs. Okay, now.
You know, Anna.
Oh, hi,
you know what's the coolest thing you could do with these kind of batteries?
What?
You put them on your tongue.
No.
You touch it with the tongue. Yeah, it tastes like metal. It's great. Good stuff.
Good stuff.
Everybody should try it at least once.
You see, Mickey, that's why I need you here. You go to places I don't. Okay, I was going to connect my circuit. Oh, let's see. And the LED lights. Okay, once you close the circuits, the LED lights up. Yeah, it's very simple. That's what that we want to do here. So, just a little joke here. the reality in circuits is that we're not going to do all these analysis. Circuits can get quite complicated as this one. But we will have the tools to really tell the computer what to do and to form algorithms that helps the computer compute. Okay, and part of the tools is linear algebra, which is something that you guys already are working on. Okay, so circuit analysis. Just a little shout out for some of our colleagues. One of the tools that is used in industry today is called SPICE, which is Simulation Program with Integrated Circuit Emphasis. This was developed at Berkeley, and once this tool, and it was developed as it started off as a project for a class, and then once the tool was developed, it was given to the world as open source. And many people use this for circuit analysis, for device. If you want to model specific devices as you come up with new ideas or you use new materials, it's a great tool to use. And then we have this amazing professor. Miki, since you're here, you want to say his name? I know you love it.
Alberto Sangiovanni Vincentelli.
That's right. So Professor Sangiovanni has actually opened two very successful companies that do exactly this, electric circuit analysis. Cadence, some of you might actually have used some of the tools of Cadence or will, and Synopsys, two very successful companies that came from Berkeley. So, go Bears! And you see our mascot also goes to the clean room, not only to the football field. All right, so let's start then. With our tools. Questions so far? No questions. All right. Now to write, I am actually, I'm going to write on my slides, and to write, I'm going to exit this mode, and I will use this because it gives me more options in colors. Okay, so let's burn some transistors. Let's define some quantities that we will need to analyze circuits. And I know that many of you will have some intuition about some of these quantities, and we'll just give you some analytical and quite a formal way of representing those quantities. Okay, let's start with the first current, the first quantity, which is current. Current. What is current? Anybody wants to share thoughts on what is a current that goes through the circuit?
Current is a flow of charge.
That's right. Current you can think as a flow. It's a flow of charge. And in circuits, the analytical symbol for current will be I. And what's the unit of current? It's amperes, yes. Also known as amps, and the symbol is A. Very good. I see that we have some good definitions of current. We'll get to that in the next class when I talk a little bit more about physics. Today, I have to ignore physics because we are teaching the computer. So, but yeah. Okay, current. The next quantity will be voltage. Voltage. Anybody has some idea what's is a potential difference? That's very good. A voltage is always measured relative to something, and it's relative potentials that you have in the circuit. How can you? What are the equivalents that we can do here? A voltage could be thought as pressure that you have going through a hose, while the water flowing through it is the current. Okay, and if you change the hose that you're using with the same amount of water, you're going to change that pressure, and you can change the flow also. So we'll see all of this related to circuits. So the analytical symbol for voltage is V. And today we are going to talk about potentials and voltage. So whenever it's not clear if I have a V or a U, let me know. Okay, and the units is volts. And the symbol is a V also. And the final quantity that we're going to talk about today is resistance. Resistance. And what's resistance? Anybody? Yes, but what's when you think about resistance, how can we explain what resistance is?
Professor, it is the material ability to impede the movement of charge.
That's such a good explanation. Exactly. It's
Anna.
Yes, Mickey.
I'm sorry, I don't want to interrupt. I just want to say that this, I do. Students are resistance. Students on the roads at Berkeley.
No, they're dopants.
They're dopants? They're not resistance?
No.
Because I hit them all the time.
No.
Okay.
They're dopants. This is upper division physics.
Upper division. Sorry.
Yes. Sorry, Mickey. Anyway, resistance. It's really comes from the material, and it's the different materials will have different properties. Some of them will let current flow through them without much resistance. Others will give more resistance, more resistive material. Very good. So resistance, the symbol that we're going to use is R, and the unit for resistance is ohms, which is represented by the omega symbol. Okay, so current always flows through an element, through a circuit element. And these elements could be just all these elements that I showed you before. Voltage, it's applied or measured across the elements. And finally, the resistance, as we had such a nice explanation here, is the opposition or to current flow. Okay, all right. Questions? Okay, so now what I'm going to do is I am going to go over some of the definitions that we need here to teach our computer. First, a circuit diagram. What's a circuit diagram? It's really a collection of elements. The little anecdotes that I had with the battery and the diode and the resistor, that is a circuit that you can draw a circuit diagram. It's here for our class. All we need to do to draw this circuit diagram will be, we can have any element here, which we can draw as a box. Can be anything. This element will have some connections. So I really want to use this so I can change colors better. Okay, so so we have leads for this element here. That would be the wires that connect this element to other things. Through the class, I am going to call, I will always define the current flowing through the element. And I am also going to define the voltage measured across the element. So these are the basic representation for a circuit diagram that we're going to use. We have the current going through this element and the voltage across the element. Okay, now let's go over and look at the different elements that we are going to define here. What did it say next to the I? Element, EL for element. Okay, wire. What's a wire? Wire can be part of a circuit, right? You also have wires in your lab kit. So how do we define a wire? So a wire, we are just going to draw here the element wire. As I did before, we know since this is a circuit element, we're going to have a voltage through the element. And we are also going to define a current, which I can use here in a different color, a current going through the element, right? If we have a wire just like this, like we drew here, what's the voltage across this element? Zero. Yeah, there is nothing across this element, right? So I can say that the voltage is zero. Right. Now, what is the current of the element? That we don't know. We only know that the voltage is zero. Why? Because the current will be set by the external circuit. All right. So the other tool that we want to have here is what is called current voltage characteristics, IV curves. Some people call it the Ohm's law, but I'm going to call it the IV characteristics of the element. How do we draw this? We're going to represent in a plot the current through the element versus the voltage across the element. So for a wire that we don't have any voltage across here, right? I don't have the external voltage source. We establish that the voltage is zero. But the current could be anything once we have the external circuit, because that's going to be defined by the external circuit. So when we draw this, we are going to get a line going here through the voltage zero. So the voltage is zero, And the current could be anything, okay? So this is our wire element, okay? All right, let's go to the next, everything will become clear. I will do slowly, step by step, because we are teaching a computer here. All right, resistor. Let's now do the same analysis for the resistor. So the resistor symbol is some squiggly line here. And first thing I'm going to do is to say, okay, I have a voltage element here across the resistor, and I will define a current going through the resistor. Okay. Now, do we know the voltage for this element? If I had to express the voltage element for the resistor, do we know what it is? Anybody? That's right. That's the good old Ohm's law. That will be the resistance given by the material times the current of the element, which we know as Ohm's law. Okay. How does the IV characteristics look like in this case? We'll draw again our plot here representing the current of the element versus the voltage across the element. And for a resistor, the response will be a line. And this curve is interesting because if you look at the slope, here of this curve, you will get 1 over the resistance. And as you increase the voltage, you increase the current along this line. Okay? So far, so good? Okay, how do you measure resistance? You can apply a voltage across, measure the current, plot the IV characteristics of the resistor, measure the slope, you have that. In real life, what can you do to measure the resistor? Well, you can also use a multimeter, and you set your multimeter. I'll show you here. I'll use myself as a holder for the multimeter. Computer, come closer. Okay. Can you see the number 1? Yes. Okay. I have a resistor here. I'll connect my probes to my resistor, which also came in your lab kit. And do we have a measurement? Maybe we need to go a little lower. Oh, better. Better resolution. What's the resistance? I can't see. $320. Thank you. Ohms. Very good. That's the resistance. Okay. I need a helper here. Okay. All right. Let's keep moving with our elements. The next element that we are going to talk about is something that you wouldn't think as an element for a circuit, but it's important to talk about. And you will see maybe one lecture from now in circuits that we will use open circuits, and we will be dealing with open circuits. So how would we represent an open circuit? Open circuit would be a break here in the wire. This is our element, open circuit. I'm going to put, just like I did before, I'm being very careful here with my definitions, voltage across the element and the current of the element, because I want to represent the voltage, the current voltage characteristics. In this case, what's the current flowing through this element? I'll get to your question, Rebecca, on the plus and minus. Okay, it's 0. Now, what's the voltage across this element? That we don't know, right? And the voltage across this element, it will be set by the external circuit. All right. So we know the current is 0. When we draw then our diagram here, our IV characteristics for an open circuit, how would that look like? That's right, Levi. It's a horizontal line because the voltage will be whatever whatever is set by the external circuit, and the current will be 0. So it's just a horizontal line running here across the current that is 0. And the current is always in amperes and the voltage is always in volts. Okay. Next element, just definitions. Set by the external circuit. It means that we don't know what's the voltage. Let's say if I have an open circuit, it means I have a wire like this, 2 wires, which have not been stripped, so they wouldn't connect anything. I could connect them to the battery like this, right? And if I connect them to the battery like this, there is a voltage applied across them that was set by this battery, but the current is 0 because it's an open circuit. Make sense? Go ahead, Ufoma.
Yeah, sorry. For the beginning one where you had like the wire and you said you applied a voltage difference, right? I was wondering why the voltage is 0 if you applied a voltage difference. Wouldn't the voltage different?
For the wire?
Yeah.
I said that if there is no voltage, okay, so let me go back to the wire. I said there is no voltage applied to it, but there could be current. We don't know. We don't know what else is there. But in the wire by itself like this, there is no. When would you see current? Oh, you could actually induce current, right? You could have a wire that's made with materials that somehow will have a gradient in charge. There are situations. This was set by whatever is outside.
Oh, okay. So the current that's being formed through the wire is not based on the voltage. It's not based on the VL thing, the voltage.
Right, but just a wire like this, there is no voltage, right?
Okay. Thank you.
Yeah, no problem. It's always good to ask questions, and because I'm sure it will clarify for others. And I can't read the chat at the same time that I'm talking. Typically, I'm reading the chat for Mickey. So, but once Mickey is back, he will do that, and then we can answer the questions as we go. Okay, thank you for the question. Okay, and there are some more sophisticated answers there in the chat also, but don't feel bad if you don't know what they are talking about, because I will take you to that level. All right. Voltage source. Okay. Now we're talking about the power sources. Those are important. We are not going to have much happening in the circuit without the power sources. Oh, the bears came, good. So how do we represent the element, okay, voltage source? That will be a circle with a plus and minus. And where does this plus and minus come from? From the fact that a voltage source, the power sources always have a polarity. They always have the plus minus, okay? That's important to keep in mind. But as I am, and this is a power source, so as a voltage source, so we will always have a set voltage. In the case of batteries, is easy to understand because we are used to it. We are used to pick up a voltage of a battery that's 9 volts, battery that's 1.5 volts. Okay. Then, but here in our definition, how are we going to represent this? We have the voltage source. I do want to have the leads just like I have for other elements. And I am going to make like a square around this voltage source, just so we remember that this is an element and we are using the same method here to understand these elements. So there will be a voltage across this element that we will call V element. And we will define a current flowing through these elements that we call VL. Okay. So in this case of the voltage source, what is the voltage? What is the voltage across this element? I'll say V element. Very good. The voltage is Vs, and that's set by our source, by our voltage source. What is the current flowing through this element? That's right. It's determined by the circuit. We don't know what the current in this element is because it's determined set external circuit. All right, it depends what else is going through, but the voltage is set. Okay, how would we draw the IV characteristics of these elements? Where I have here E element, where I have I element. How would that look like? A vertical line, but positive. That's right. It would be a vertical line that crosses VL at which point? That crosses, that's right. So it will be a vertical line, as vertical as I can do here on the roll, that crosses VL at VS. Very good. See, not complicated. I don't know who told you circuits are complicated. Just language. We are getting the language right from the beginning, and then everything will be just fine and fun. Okay, how do we measure voltage? Oh, with our multimeter here. We set the multimeter to volts at some reasonable range. And okay, and then here my super duper apparatus here. Let's start with the 9 volts batteries. And that is a good way of knowing if you have a good battery. Okay, oh, my hand is going. Okay. Well, what's the measurement I get? 9. Am I getting a positive measurement or a negative measurement? Negative. Why is it negative? Oh, because I switched the polarities here. So let me turn around. Positive now, right? So someone in the chat said, OVS should be positive. If I connect things correctly, it will be positive. If I make a mistake, connect things the other way around, the sign will be different, but the voltage is still the same. So when we do our circuit analysis, sometimes we'll get a negative sign somewhere, and that negative sign is just an indication that the direction was not using a convention. Okay, now another battery, different battery. Let's see if I can hold the leads. Yeah, what do I measure there? Again, negative. Minus 1.5. Okay, this is a good battery when I put it apart. Okay, I took some batteries out of our snap circuit. So, okay, this one. 1.2. Oh, bad battery. This is good for a mouse or something. All right. And I had the polarities wrong, right? Because it was just the way I could hold under these conditions. Okay. Very good. Yeah, I have some demos with snap circuits later on in the course. Great. Then let's continue here. Voltage source, any questions? Okay. Let's keep going. Let's keep cranking on this elements, because at the end we have a nice circuit to do some analysis. So current source. So the current source, similar to the voltage source, will be, we draw a circle, but now we're going to have the symbol here, current, going through, not the plus minus. And that current source is going to give us a fixed current, which I'm calling IS for current source. And okay, and it's an element in the circuit. So keeping with our method here, to not confuse anyone, I'm going to put this transparent box around it so that we can say there is a voltage element that is across this element, and I'm going to define that there is a current element going through it. Voltage across, current going through it. Now you should be getting the idea here on what we are doing, since we're always doing the same thing. What is the current element going through a current source? Wonderful, IS. This is fixed by the element. That's what the element brings to the table. And what is the voltage element in this case? Very good. Set by the external circuit. Okay. Very good. Let's do the IV characteristics. So if I do here our plot, V element, I element, how would this plot look like?
It would be horizontal on the y-axis, depending on the current.
Right. It will cross the current axis at which point?
Current S, IS.
That's correct. Something like this, right? Oh, okay. Now, one thing that I should I should say here, and in my demo here with the battery, right, was clear, is that the voltage element and the current element can be positive or negative, right? It really depends on how we are defining things. So if I have a rule that I say, oh, if I connect things this way, I say this is positive. If I connect separately, it will be differently. It will always be negative. That's the convention. Then I can be consistent. And that's what I have been doing here. I've been consistent in our convention, right? But in real world, it can be positive or negative. And there was a question here. In real world, is there current sources? Yes, there are current sources. In some cases, you need a current source and not a voltage source. Okay. Shreya, if I cannot answer direct messages, so, but you can come to office hours later. And okay. All right. Oh, an example of a current source? My favorite of all, a solar cell. Solar cell is a current source. See, learned something today. A solar cell is a current source. Okay, and the current from solar cell is called short circuit current. And you should come to 134, EE 134. I teach all about solar cells. Oh, I miss them. Okay, now let's set rules. Circuits have rules. Computer likes like rules. If you follow the rules, the computers work. Okay. So the first rules that we are going to have here is Kirchhoff's voltage law, that is referred as jargon KVL. And it's a very nice rule, and we are going to use it a lot. What does this rule say? It says that the sum of the voltages across the elements in a loop, and why do we care about loop? Otherwise, it's not a circuit. Circuit has to be a loop close, equals 0. So all the voltages across, going around the loop, a circuit, are going to be 0. I'm going to use a simple circuit here all the way to the end of the class, where we are going to set up our equations to solve this circuit. Okay, so I'm going to draw here a voltage source that is connected by wires to a resistor, and I'm going to close the loop here. Okay, now, how many elements, circuit elements, do we have in this circuit? We just went through the definitions of all the circuit elements. Some people say 2, some people say 3, a few people say 4. 4, we have 4. We have, oh no, don't do this to me. Okay, we have one wire here. We have a resistor here, another wire, and a voltage source, 4 elements. And I'm going to be repetitive and pedantic here for the teaching purposes, because I want this to stick to your mind, okay? And then we will simplify things later. All right, so I know from definition that the voltage source is going to provide a set voltage to the circuit. And I know that a resistor will have a set resistance to the circuit. Now, I'm going to apply KVL around this loop. We can choose whatever direction we want, but I will do here, start here on the lower left corner. But before I do that, I will set the voltage and the currents through these elements. So I know that there will be a voltage across our voltage source, which I'm going to call V. Okay. I give up. I'm going to call V element 1. Okay, and there's a voltage across that. Then our second element here, which is a wire, I'm going to call element 2, and I know that there is a voltage across V element 2. Same thing. Oh, let me give the number. There will be a voltage across the resistor, which I'm going to call V element 3, and a voltage across this wire that I'm going to call V element 4, and also define the signs here. Okay, now let's go around the loop and see what the sum of these voltages across are going to be. If I go from negative to positive, I'm going up in potential or down in potential?
You're increasing in potential.
I'm increasing the potential. So I'm going to say when I go up in potential, it's positive. So I'll say V element 1. Now, going around now I'm going to go V element 2, right? Here, V element 2. I'm going from positive to negative. So convention says, what's that voltage? Positive or negative? Negative, a drop in voltage. That's right, minus V element 2. Keep going in the loop and the resistor, positive or negative? Negative also, minus V element 3. Again, in my wires, positive to negative minus V element 4 equals 0. This is what KVL is all about. We go around the loop, we follow the voltages around, and we know that the sum is going to be 0. Why? If I had to represent separately, I would say, okay, here is my VS, where I went from negative to positive, and then I had a voltage drop V element 2, a voltage drop V element 3, a voltage drop in V element 4, right? It's like when you go skiing, you go to the top of the mountain with the fastest ski lift possible, and then you come down, lose potential, come down, lose potential, but the total is the same. All right, questions? Okay, we have a hand up, full man.
Yeah, so for the voltage increase, is it just, it's only going to be the wire that connects with the voltage source and everything else just decreases?
We will see, we will see. Can you hold that? We will have many examples. I don't want to give like generalized answers, yes, and then other examples that are not. But of course, if the voltage supply is our voltage, we are not going to be creating voltage here, right? Mm-hmm. So, and that's what this law is all about. So if I give you a voltage supply, then all the other potentials that will be dropped through the elements will have to sum that voltage supply, because we're not, we don't have another voltage supply.
Okay, thank you.
Increase that, yeah? Okay, Darren.
Hi, Professor. So if we were going from the negative to positive side, we would be subtracting from V element 1, right? So if we went from the positive to negative side, would it be adding on, or?
When you go, when you add potential, when you go to from negative to plus, right? That's I'm adding. So and whenever I go from low to high, I'm adding, right? And then if I go high to low, because it's a potential, high to low, I'm losing. So that's why it's negative.
Right. So the equation written in the red one is for going from positive to negative, right?
It's for throwing this loop here. I went from negative to positive, positive to negative, positive to negative, positive to negative.
Oh, okay. All right. Thank you.
No problem. All right. Let's keep going. And now, that's why I didn't want to use this, because it doesn't let me like this. Keep. All right. I will try this one with Cal. Okay, second rule, second law. Now it's also Kirchhoff's current law. And here it says that the current flowing into any junction must be equal to the current flowing out. What are junctions? Junctions are the points where we connect the elements. So in our circuit here, we had a big junction here, terrible junction. Inside elements, there are junctions because especially in a diode is a junction of two materials, p-n junction. So inside there are junctions. So the current that comes into an element has to be the same that is flowing out of the element because there are junctions there, and in any junction between elements also. Okay, so if we draw our example circuit here with a current source, which I'm going to call IS again, and that same current source is connected to a resistor like this. And now we have our four elements, a wire, resistor, another wire, and a current source. I'm going to name all the voltages and the currents again. So we will have, okay, V element 1 here, and a current element 1 here. I will have voltage V element 2 here, and let's define a current going through element 2, I element 2. Then voltage drop here, V element 3. We know V element 3 is a resistor of resistance R. And then we define I element 3. And our final element here, our second wire, V element 4. And we will define a current I element 4 going through this element. Okay, Darren, your hand is still up, just so you know. Okay, now let's apply KCL, which we are going to apply KCL a lot in this analysis to all elements. So through KCL, it says the current that is flowing into a node has to be the same as the one that is coming out. So we have a node here in the corner, which will give us this I element 1 is equal to I element 2, this node here. Now, this node here, we were going to write I element 2 equals to I element 3. In this node here, we have I element 3 equals to I element 4. And our final node, we could write I element 4 equals to I element 1. Do we need this last equation for this analysis here? No, Alex says no. Why, Alex? No. That's right, it's redundant, right? We had 4 nodes, so we only need 3 equations to describe those 4 nodes. See what you learn in linear algebra? It's coming here. Okay, another way of writing this is we can write that I element 1 minus I element 2 equals 0. Okay, and the same for the others. And then when we do this, we are already putting things in the shape that we learned before. Okay, questions. I have a question. They are not Christian, but we will get there. Okay. I have a question for you. What if, let me pick a different color here. What if I had said, when I was setting my circuit here, that I have I element 2 this way? Element 2, I element 2. Different direction. What would happen in that case? It will be negative. Exactly. It's different direction. I'm going from minus to plus, right? So I would say, in applying for that junction, I would say, following KCL, that at that junction here, if the direction was different, oh, this is really thick, I would have I element 1 plus I element 2 equals 0. Why? And element 2 is negative because it's in the opposite direction. So in some cases, when you do your circuit analysis, you will see that you have a negative sign somewhere. Important thing is to keep track of the conventions. A different example of this, let me do this. We could have a circuit that looks like this. 3 resistors, or 3 elements, I'll put here. I'll put 3 resistors that are connected this way. So right here in this junction, where the 3 elements meet, I would have, okay, I element 5, I element 6, I element 7. And when I write this, what would I say? The current arriving at the junction had to be equal current leaving the junction. So in this case, I would have I element 5 plus I element 6 equals I element 7. Could still write in an equation form equals to 0 if I take the element 7 as negative. Okay, very good. Oh, good participation in the chat. All right, let's keep going. Now, more rules, more rules. There are rules within the elements. I have already told you this. So when you are, but I will write down so it's clear to us. When we have our elements, our generic elements, I have been always here putting a voltage across and a current across, right? Now, what we have to do here, so I have V element this way, and then here, B element this way. When I define the current, I can define a current that is going into the element, I element, like this, or coming out of the element. And that's what KCL is within the elements. So this is the same thing, right? It says the current coming to a junction has to be equal the current going through another junction, where the junction now is whatever is inside the element. Okay, so they're both allowed. It's the same current. Okay, lots of rules in circuits. We just have to obey them. Stick to our convention. This one is pretty useful, and we are going to use it a lot, especially as we move on to more sophisticated circuits, which is called the passive sign convention. What is the passive sign convention? Very, very simple. It just means that when I have been defining the elements here for us, I had voltage across, and I was always putting this plus or minus, right? And then when I define the current, I was very careful to say, okay, here's I element this way. And that just says that the current arriving at a positive terminal will be positive. And you can also represent this element with the current coming out of the element. Like this. So they're both allowed. That's what's the passive convention, passive sign convention. If I do it wrong, then we will have consistent problems with our signs. Okay, let's do the algorithm now. We only have 4 minutes, but I think we can start. Now the rules for an algorithm, which are connecting to the algebra now. So let's take our circuit here. And I will give you a simple, a very simple circuit. I will not turn things upside down to confuse anybody. Okay, which will be a voltage source and connected to a resistor where I have Vs and R. And here, first thing, find current through the elements and the potentials of input and output of each element. What's the potential? The potential is from each element will have a voltage across, which is the difference of those potentials. So I'm going to say here, okay, starting here, I have potential 1, potential 2 going through the wire. And then here, going through the resistor, I'll have potential 2 and potential 3. Going through our second wire, I will have potential 3 and potential 4. And then through the voltage source, we will have potential 1 and 4. So those are the potentials. Now, voltage is the difference between potential. So when I look at my wire here, and I say, okay, there is a voltage element 1 here. What is this voltage element 1 going to be? It's going to be the difference in potential. So it's going to be potential 1 minus potential 2. That's the difference. And I can go through all these elements writing the same equations. But somebody already said, oh, it's a 0. Why is it a 0? Because it's a wire, right? So if I have a wire here and I have a wire there, why did we define all these elements, right? What did we define in the wire? We said key element, wire, the voltage is 0. So I can say that voltage element 1 is 0 because that's the characteristics of that element. So I know that U1 equals to U2. I'll finish this. And then, likewise, I have another wire here. So I know that U3 equals to U4. So what I will do, I will just call this potential here as UB, and the potential, let me use red, UB, and the potential through the wire, the top, UA. Now, that means we only have 2 nodes in this circuit. And there was a question, are the junctions the same as nodes? No, we have 4 junctions in this circuit. But what are the nodes that we have? We have, the nodes are where I can connect 2 elements. So here we go. Here's a node, one node. Then I'll pick another color here. And here's the other node. So when I solve this circuit, I have to solve the circuit for these two nodes. And what are my unknowns? My unknowns are the potentials, the resistor, typically given, the voltage is given. So now I have to solve the circuit for the potentials. And since time went too fast, this is where I'm going to pick up in the next class on circuits, which will be next Thursday. Okay? But by now, you should have everything you need to follow the discussion. No, Tuesday you'll get a little bit more linear algebra, but that's okay, all good stuff. Okay, be good people out there. Take good care.
All right, thank you, Professor.
You're so welcome.